AB Calculus, Note Card 49, Definite Integral. And this is the 49th video lesson in this series inspired by Stacy McMullen, formerly of the Dallas Independent School District, who developed this note card system. And this is our second that has to do with really integral calculus. Definite integral and interpretation of a definite integral. The definite integral of a continuous function f over the closed interval from a to b is the limit of Riemann sums as the widths of the subintervals approach 0. The definite integral for subintervals of equal width is given by, and we have on the left a notation that I am really quite familiar with. This is the integral, the definite integral notation, and to the right of that equal sign we have the Riemann sum notation. And I am somewhat familiar with this part of the notation here in that during my years of teaching pre-calculus, we have gone over this as part of our scope and sequence. But we're going to use this to work a few more problems later on in the session. And here we have the different pieces. You see this x, this delta x of I is going to be replaced by this b minus a over n, and so on. And this a plus I, x of I is going to go up in here, but we're going to go over that here shortly. The first one we're going to look at here is a calculator free response problem from an earlier AP test. The table below, v of t represents velocity in feet per second. And this is what we call a rate of a car traveling on a straight road. And we have a table with values, and it says, A, approximate the integral from 0 to 50 of v of t dt with a Riemann sum using the midpoints of 5 subintervals of equal length. Now, to eliminate the rate, we need to integrate. And so we're starting out with feet per second as a rate. And so our answer after we integrate is going to be just feet after integration. So I'm just going to put here feet at the very end of my answer, knowing in advance that that's what my units are going to be. So approximate, so we're going to write this out and say approximation of 0 to 50 v of t dt is equal to, and we have 5 subintervals. So I'm going to write this out as 1, 2, 3, 4, 5, and that many, after we add these subintervals together, feet. Okay, now let's look at the data here. We want to have 5 subintervals, and to have subintervals with a midpoint, we're going to have an odd number of values. Let's try 3. If this is our first subinterval, and that'll be subinterval 1, we'll call it, and then between t equals 10 and t equals 20, that's going to be our second subinterval. Between t equals 20 and t equals 30, this is going to represent our third subinterval. And between t equals 30 and t equals 40, that's going to be our fourth subinterval. And then between t equals 40 and t equals 50, that will represent our fifth subinterval. And then we want to have our delta x is going to be 10 apart. So our delta x is 10, and each one of these intervals is 10 apart, 10 seconds apart in time. So we put 10 out front on each of these blanks And then what we're going to do for midpoint is find the mid value. So our left value would be 0, our right value would be 20, but our mid value for this subinterval is 12. Put 12 here. For the second interval, our mid value is 30. Oops. For our third subinterval, our mid value is 70. For our fourth subinterval, we have 81 as our mid value, and then our fifth is going to be 10 times 60. And these would be quite easy to add together. We'd have 120, 300, 700, 810, and then 600. But we don't need to do that because this is a perfectly acceptable answer according to AP standards. Using correct units, explain the meaning of this integral. Okay. Well, we just need to change to English. So during how much time? 50 seconds. The car travels or traveled. Or you can say travels or traveled, either one. This many, you can see what I'm going to do. And I'm going to just go arrow here and just circle all this. This many feet, just pointing to it. There we go. And that would be our explanation of the meaning. Next, problems 2 and 3. If n is a positive integer, write the definite integral for each of the following. And here we have our Riemann Sum notation, with which I am not as familiar. And so I have made another slide below that has sort of a guide from the note card that we're going to use to sort of piece this together as a definite integral. So I'm just going to write below here a definite integral, and we have we're going to need to find these pieces to get this right. And the first thing I'm going to look at is this thing right here. Okay, this thing is going to be equivalent to our, it says delta x sub I is equal to b minus a over n. Okay. So we have that piece to reckon with. And then we have this piece here, that x sub I equals a plus I delta x. So here we have, according to this should be our a, right? Which equals 4. And delta I is this, and we have 3 over that. So we're going to have, our function is going to be 1 over square root of x. Okay. So we're starting with our value of a down here, which is 4. And then b minus a is in the numerator here. So to have 3, so if 3 is equal to b minus a, okay, let's see, then a is b minus a equals 3, so b minus 4 is equal to 3, so b therefore is equal to 7. So we're going up, we're integrating from 4 to 7, and then we have 1 over square root of x dx. And really, that should be it. I hope this makes sense, and I hope it's right. Let's go on to number 3. Here we have the same type of situation. We have in this b minus a over n, we have 2, and so we're going to start our integral here, and our a value here appears to be 7, because in this a plus I x sub I, so that's 7, and then b minus a is 2, and so 9 minus 7 happens to equal 2, so that's what it looks like. And what is our function going to look like? We've already added this a, but inside we have, looks like 5 plus x to the power of 3 dx. So this is as best as I can ascertain right now. I hope that's right, but you can see, I hope, how I followed the logic here using this guide, this informational guide. Let's go to problem 4, the last one we're going to look at, which is going in the opposite direction. Express the definite integral from -2 to 3 of 3x minus 6 dx as a limit of Riemann sum. And I happen to have got the next slide, which has below this guide with which we are going to work. And what that's going to equal to is the limit as n approaches infinity of our integral here. And we're going to start out with I is equal to 1, and we're going to go up to n here at the top. And then what we're going to have is we're going to have a plus, so I'm going to go put a value of -2, that's our a value, and then we're going to have replace the f of x, we're going to say a plus, which we already did, I delta x, well that's going to be 3, let's see how we did this in the other problem, cheating back here, 3i over n, okay, we're going to write that as 3 I over n, and our n value is going to be 5. Why is that? We're going to talk about that in a minute. And we're going to subtract 6, and then we're going to have times n over b minus a, which we have 3 minus -2, and that's going to simplify to 3 to n over 5, and what do we have? Well, I forgot something. Okay, it's going to be negative 2 plus, because we're adding, yeah, a plus, and then we're going to treat this as a, okay, it's just the notation of it. And then I'll just double parenthesize here. And so really, that's it as best as I can figure out. So I hope this has been helpful to you. Again, this is an area where I'm really not too solid yet, but I'm learning as I go. So good luck as you grapple with this, and thanks for viewing.